of everybody's purview, and yeah, most people, this is going to be a very sort of introductory thing, because most people, even if they're very well versed in neural networks, like they're not exactly sure what a spiking neural network is, where the transition goes from one to the other, where they come from and what they're used for. And so, yeah, the data analytics side of this, sort of as the group, is formed around, it's going to be rather lightweight tonight, because I don't do a lot of data analytics stuff. Most of my stuff is kind of experimental research as far as AI goes, and I do a lot of modeling on computational neuroscience side. So that's where this making is going to be. But I mean, I have this, and I think most people, shouldn't say most, at least most of the literature that writes about spiking neural networks, people who come out of the traditional AI sense of artificial neural networks, they write like spiking neural networks are the thing that everyone's going to be using in so many years from now, because they're far more biologically real. And
do you have to have a neuroscience background to understand?
No, you don't. Although it just depends on how far down the rabbit hole you want to go. Most people who use them for AI or even for some, data science work, probably don't have a strong neuroscience background, because you, just like a, artificial neuron, you can just ignore where it comes from and just use it as a bunch of collection of functions and classes and wire it up like anything else. We'll talk about it a little bit whenever Isaac wants to start.
Yeah. What song is it?
5 past, if that thing's right.
Yeah. We can wait like 3 or 4 minutes.
All right.
Yeah, particularly me and Mark, we have that habit of just start around 7:15 or so.
Okay.
Some people drive along. For what?
Android.
I don't.
Standard micro USB.
I don't think I have one in my bag. I usually have one on here.
Would one of these work?
Yeah.
Oh, this seems like mine. That's all right. Thanks.
So who do you work for?
It was for me.
Oh, you do?
Yeah, I do. I work as a data integration developer. So the university, in the long range, is looking to develop analytics that can benefit students in multiple ways, like helping them with succeeding on their courses, completing the degree in less than 6 years or 4 years. I don't remember the metric.
Yeah. They always say they want everyone to finish in 4 years. I would be surprised if, like, behind the scenes there's for 6.
Yeah, there's like a bunch of items. Essentially, they want to make the university the most ideal place for students by using analytics.
Yeah.
So my job is to develop data marts, develop like a mini data warehouse, populate that with some ETL jobs, and hopefully create a unified view. So that can help in planning for the university. So if they say, oh, we want you to finish up in 4 years, then you have to offer the right courses at the right semester.
Oh, I see. Almost like, so there's scheduling stuff involved as well.
Yeah. So, and another thing, recently the UMS, the entire system has 7 campuses. They all started to unify into one.
Yeah,
so they want to also, so this solution, whatever we develop, needs to be deployed across all campuses. So that's a very limited information.
Yeah. But it's important, to look at data rules the world right now.
Yeah, there's a lot of information that can be benefited if it is like integrated and the unified view is created. So they can do course planning, degree planning, student success, and all that. They have a list of items. They want to do all this to students. They want to roll it out. So the students are benefiting from all the analytics stuff like that. But we are on step 1 or something like that.
Of
just get
27 steps.
or more than that. We are very, very behind.
Oh, everybody is behind. Especially in the computer world, in the programming world, we're always behind.
Yeah.
Nobody's behind.
MIT is pretty ahead of us.
They say they're ahead, but they just have a lot of money to hide how far they are behind too.
Wow, that's a profound statement. I'm telling you. It's just struck me. Your name is Zach?
Yeah.
Okay.
Yeah.
So what is Hudson Bay Company?
It's basically a large retail conglomerate. You don't know them probably, but you probably heard some of their brands. They actually own like Lord and Taylor, Saks Fifth, some of these high-end like clothing brands. Particularly well known in New York and stuff, but that's where. But anyways, what I do is basically all the data comes both from the stores and online. And then so I develop so
Inventory?
Yeah, inventory, like stock in stores, how much stock should be reserve.
Optimization.
Yeah, that basically. I also do some natural language processing. My specialty is actually natural language processing. So I'm also mine like text data, like similar products together, and things like that, and I'm using the unsupervised cluster and using that. I'm hoping to work on a chatbot soon. Hopefully that will get through because actually, particularly dialogue is kind of an area I like researching, but I have no idea that will actually do. But yeah, that's kind of
When you say approval, what part of approval?
Every project we work on has to be approved by like the VPs and
it's
HR.
for the company.
Yeah. Yeah. So me and a couple others wanted to do a chatbot for a while so that like if customers would be on the site, they could ask questions and stuff. But in order to actually put in the man hours and all of our expensive salaries towards working on this thing, we need to develop a plan, and the VPs need to sign off on it. And we need to show there's better use of resources than say just having to show the SQL all day or something.
I thought that at first I thought you were just talking about research. You were just
Yeah.
okay.
Very cool.
Okay. Yeah, I guess you can get
This work. Slideshow. Come on, thingy. Wait up. I think it's this button. Yeah, that's pretty good. All right. So as the title says, I'm going to talk just got a few slides about spiking neurons and spiking neural networks. This is, like I said, it's more of a 101 type discussion. So don't, feel free. This is not, I don't want to just sit here and talk the whole time. So
This is being recorded.
I have no idea. Probably.
Is that something on top?
Yeah. So this is recording now.
Okay. All right. So, but if you have any questions, just interrupt because I don't want to. I'd rather this be more of a dialogue thing since there are only 3 of us. Blah, 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 blah. Oh yeah. So first thing I wanted to do was actually not look at slides. So I'm going to run a little code here down. If it breaks, don't worry. That's not what I wanted to do. Because I wanted to give you guys a little bit of what it looks like to run, what spiking neuron behavior is. Like, how does it differ from an artificial neural network, which we can kind of talk as this thing is running.
It's all C code. Or?
It's all C++. It's C++, yeah, this is all C++. So yeah, there will be a lot of Python in today's discussion. So I know you know what an artificial neuron is. How familiar are you with like the components of a neural network?
What I recollect is, there is that layers of processing layers, and each layer is multiple linear combination of items. And then I guess you add more layers for greater accuracy or something like that.
Yeah, I mean, that's even already a very big picture of adding layers, but at the very small part, right, there's these individual components that have input coming into them either from outside the network or from the previous layer. There's usually a sense of a threshold.
There's a vector and the magnitude.
Yeah, and then there's some sort of combination. Either it's just a sum and you pass on your value, or there's a sum and then like a sigmoid squashing of the values to where it's between 0 and 1 or -1 and 1. There's all kinds of stuff. So that's what an artificial neural network is. It's just, you know, a combination of values and spitting out something on the other side. A spiking neuron, if you were to draw a simplified view of it, it would look exactly the same. But what happens is, as you can see here, this blue line is the actual membrane voltage. So what you do with spiking neurons is you have a voltage modeling, a value modeling the membrane voltage of the neuron. And it's very analogous to what happens in an artificial neural network, except for when you reach a threshold value. So what I'm doing here is, if you can't see it because it's very tiny, but on the upper left-hand corner, I'm increasing the input to this neuron. There's one neuron here. You can see that the blue line is rising slowly. And once we hit a value somewhere around 52 or 53, this thing will begin to emit spikes. I think it's going to happen, yeah. So this is how a spiking neuron behaves. And it's an integration of input over time. So
what does the spike indicate?
The spike indicates that it reached a threshold value. So just an arbitrary threshold. You can set it to whatever you want. I believe this one is set at something around -35 millivolts, something like that. Don't worry about the specifics of all of the details, but all you need to know is that the input coming into the neuron is summed together and processed through several differential equations, which calculate this voltage value. And as you know, as you can see, like there's a space between each of these, right? So there's several different things going on here. One is a differential equation that's controlling the membrane value, the membrane voltage. And then whenever there's a spike, there's a reset. So you can't have this equation just continue because it's a function and it would just skyrocket and run out to infinity. So whenever a threshold value is reached, there's a hard reset. As you can see, it just goes back down. That's actually just an if statement saying, if you're above a threshold, produce a spike and reset yourself to this value. And there's an interspike period where no matter how high you jack this input up, what did I do? No, here we go.
So if I may ask you a question.
Please ask all you want.
So if I were to use your algorithm to calculate global minimum or maximum for a linear equation or linear program.
Okay.
So what does this spike mean in that context?
It's a very good question. So let's say you had like a network of these things put together that, you know, in an artificial neural network sense, you're trying to
find a global.
Yeah, you're trying to find a minimum or something like this. The problem here is, what we'll get to in a minute, is this hard reset. So that hard reset makes this whole thing a discontinuous function.
Oh,
yeah, it makes it a discontinuous function, meaning that all the traditional learning stuff you would do a neural network you can't do with spiking neural networks, because you can't differentiate these functions. You can't use the chain rule to do backpropagation or any of this stuff like they do. So learning is probably one of the biggest open questions, and there are methods people use, but they're not near as good as the ones people use for artificial neural networks.
So is it like this is being spiking neural networks are utilized for solving broken functions?
Well, they're utilized. I mean, we'll get to some of this later, but
sorry.
No, it's fine. No, it's good. It's good because we'll answer them hopefully eventually, and then whatever comes out of this, we can just sit around and talk about it. All right, so that's that. I listed a bunch of different types of. There are dozens and dozens of spiking neuron models, and all of these. The reason why they're very hard to integrate into artificial intelligence research is because they all come out of neuroscience. And the neuroscientists don't care if they're useful. They only care if they model the real world to some good degree, and then we'll stick a bunch of them together to make a brain model and see what comes out of it, to see if it predicts reality. Because you can't stick electrodes in the human brain, and it's also very expensive and hard to do it into animal brains, which they do a lot of still. So computer modeling is really one of the strongest tools that neuroscientists have to investigate properties of the brain where there's evidence of what happens, but they have no idea how it happens. So you take these neurons and you do the best you can by wiring them together, and then you see what comes out of it. You see what behavior comes out of it, and you try to match it to experimental data. So these things all come out of computational neuroscience. They date back to the 50s and even older. Integrated fire neurons, I think, were the first one on the list. Date back to 1920 or so, or 19 teens or something like that. The difference between them, I wrote a little bit here. The first one only retains a membrane potential. In other words, as you saw with that spiking behavior, it didn't have a reset. So whenever the input moved the membrane potential up, if all activity stopped, the membrane potential stays the same. Leaky integrated fire says that's not how real neurons work. In fact, that if input stops, they slowly decay, their potentiation decays.
Well, why does it have to be reset?
It has to be reset because there's no other way to model this spike that happens in the brain. So the differential equations they've come up with to model how the different inputs affect membrane value with capacitance and resistance and all the different neurotransmitters and the chemical agents going on. It has to be reset because if not, it doesn't produce that sharp spike. That equation would continue to grow and grow and grow. As you see, once it reaches the threshold, that threshold usually signifies that within a short period of time, the output of this equation is going to go to infinity. It's a greater than exponential increase.
So it's like, if you talk about humans, for instance, if I'm looking at something, I like, then my good side of my brain has a spike because I like what I'm looking at, like this bottle that you have. So I have this neuron spiking up.
Yeah, I mean, all neurons in your brain are spiking all the time. And there's different regions that are supposedly doing different things. Different neurons spike for different reasons. So your eye sees something, that signal goes to the back of your brain, into the visual cortex, the early visual cortex, and starts causing spiking behavior in those neurons, which cascade forward, and there's recurrent behavior, which goes backwards. And then eventually it reaches the front of your brain where they think the higher concepts are located. So there's a cascade of information, and it works really fast. So between the time you see something until the time memory starts to coalesce, there's so much going on, and it's massively parallel to where it's just a few, maybe hundreds of milliseconds at most before all of this comes together.
Sorry, I didn't mean to.
No, it's good. I like conversations like this. I don't like standing up and just going blah, blah, blah. Because who says I put it together the right way? Probably not. So the third one is one of the older ones, Hodgkin and Huxley. Those were two guys. This is a crazy computationally expensive algorithm. It models every single ion that moves in and out of cell membranes in order to produce the electrical charge. No one uses it except not even in neuroscience modeling. The last one is the one I used, and the one that you saw in that little spike in behavior. A gentleman about 10 years ago came up with a pair of differential equations that don't actually model ions moving in and out of the cell membrane, which the other ones all do. They're very sort of physics models, chemical models. This one is just a pair of differential equations that don't have any bearing. They aren't derived from reality. They just produce the same behavior. And they produce a lot of different behaviors. In fact, that example that I had up earlier, there's a bunch of different neuron models programmed into it. So you could scroll between them and see the different spiking behavior that different configurations of that equation would produce. So each of these equations has something like 13 constants in it. You configure those constants and you can get different behavior. Again, it's not all that, to the side. We don't need to worry about that now. So the question is like, how good are these things? And I stole this from this book. I saw this a long time ago and I thought it was pretty cool. So this is just a leaky integrated fire neuron, one of the ones from the list. And there's two lines here, which are kind of hard to see. There's a very faint line and then a darker line. And so what they did is they took the same voltage and they applied a voltage to a real neuron in the brain, mouse brain, I think. They applied the same voltage to a leaky integrating fire neuron. And here's the membrane voltage as they applied this input. You can see that they're almost identical, the two lines. So in other words, these neurons are very good approximators of real neurons in the brain. Only two cases. Here's one case where the fake neuron spiked and the real neuron did not. And here's one case where the real neuron spiked and the fake one did not. So they actually do a good job of mimicking real world neurons.
For what coefficients? Like you said that has like 13 constants.
Yeah. This one is different. This one has fewer constants. I mean, if you want, I can.
Well, I guess what I'm getting to is that so the simulation that it's juxtaposed on top of your rat's neural network here.
Yes.
So that simulation model must have been run with a certain coefficients.
Yeah, I'm sure they tuned it. I'm sure they probably played around with it until it.
And they used the same coefficients to create electric signals that was given to the rat.
Well, from what I remember reading this book is that this graph was made by the input is the same, but I have a feeling you're right that the equation itself, they probably had to tune in order to either shift it up or shift it down or to get the behavior that they wanted. And that's very common. So in my research, my computational neuroscience research, one of the things you do is you build a model, like the hypothesis goes into how do I build a model? What do I put into it? So you build a model based on everything you read, and then the first go round, it doesn't work at all. And so then you read some more and you change some things. And then eventually you set all of the parameters. You say, the model is good enough, I'm not changing anything. And then you only leave a few of them free to play around with in order to produce different situations or scenarios. So when I first started doing this, one of the things that I had a hard time with was imagining how real neurons are connected. And this is probably the biggest difference, other than the spiking part, between artificial neural networks and spiking neural networks, is how are they connected? Because connections in artificial neural networks are pretty much non-existent. Like It's just a lookup and an index and an array of what value am I reading into this neuron. So here's a synapse, and this is one neuron, and the neuron is actually all of this straying down to this little hole here. That's one neuron, and this is another one here with all of these little things. So the only place that they connect is here, which is blown up in this synapse. So this is the presynaptic neuron, means it's before the synapse, and here's the postsynaptic neuron. It's after the synapse. And generally, and this is certainly, the biology is far more complicated, but just like in an artificial neural network where you have information in this layer flow to the next layer, most things are modeled and set up where the spikes happen in this, and then the information flows down through the axon and then across the synapse, where it's converted into chemicals, converted back from chemicals, and then affects the next one.
So when you're actually programming these, do you have like say a weight matrix like we would?
Yeah, you can do it that way. You can definitely have a weight matrix. Most of my stuff, I end up having like matrices with complex structs inside because I've got like 10 different things that are going into it and not just a single weight. But yeah, the setup is very similar. It's just about the values you would recognize, but what happens is there's actually computation going on here between the two. That's one of the biggest differences. So it's not just take the value, scale it by a weight, throw it to the next thing.
Yeah.
There's a computation, and we'll get to that in a second, because learning, the typical way you do learning in spiking neural networks involves both things, not just a back propagating signal. And I guess in fact, that's not neural networks. I think this is sort of a repeat. What did I put here? So yeah, information flows this way. In biology, it actually also flows the other way too. So yeah, so when you model these things, I guess we were just talking about, the synapse models can actually be, depending on what you tend to do with them or what you want to do, they can be more complex than the neurons themselves. In fact, most of my stuff is getting to where the neuron models are no longer changing, and I'm making the synapse models insanely complex, because that's where all the awesomeness happens. That's where all the memory is stored. That's where all the dynamic.
So that's the part between one neuron and another neuron,
Like this
small gap.
Yeah, that's the small gap, and I've blown it up here to show that it's a thing in its own right. But synapses, neuroscience is finding that synapses are far more important than they ever thought they were. They used to focus on spikes, and
so that creates
transformations that, whereas in an artificial neural network, you increase the weight or shrink the weight, the same thing happens here, where memory is stored in the synapse. Like the weight's increased, the weight shrinks. Synapses become fatigued with too much. If the presynaptic neuron spikes all the time, synapses can actually fatigue so that they no longer change.
So how is that actually being modified? Is it like you say have a loss function at the end and then it's pushed back, or is it on the forward pass that it?
Ah, so you mean the actual learning part?
Yeah.
All right, so here we go. Perfect. Well, first of all, there's no one has this answer. There was a guy named, I think his first name was Donald Hebb, in the 40s or 50s, who first came up with this idea that neurons, you may have heard this, neurons that spike together, wire together. This idea that correlated activity between two neurons causes synaptic increase. So it causes potentiation, causes the weight to increase. And ever since then, that theory has dominated.
Wait, synapse is the gap between those two neurons.
Between the two neurons, that little tiny gap.
And if the correlation between the two activities of these two neurons increase, then the synapse is effective for it.
Yeah, let's see if so here we go. So I'll go back to the other slide. but yeah, this is called Hebbian learning, after Hebb was the guy's name. And it's also called, in more modern parlance, it's called spike time dependent plasticity. So in other words, the learning is done based on the timing of the two spikes of these two neurons. So in our simple case, our synapses sit here in the middle. Didn't draw it for some reason. And here's neuron A, just connected to neuron B, and this is the upstream neuron, or the presynaptic, postsynaptic, or downstream. So information flowing this way. So there's actually more possibilities, but I just wrote these 4 possibilities because they're the ones that come to mind. So within a short time window, so you set a time window generally for these things, because you don't want to say this neuron spikes, so A spikes, 5 minutes later B spikes, and you say, oh, well, there's some correlation. Well, that's 5 minutes. It's an eternity in the brain. So there's no correlation. We're not going to worry about that. So we set a time window where these things have to happen within. Typically, that's 30 milliseconds. That's what most people use. But you can use longer, 100 milliseconds, whatever. So neuron A can spike before B within this window. You can have B spike before A within this window. None of them can spike within this window, or only one of them can spike within this window. There's also a 5th possibility that they both spike simultaneously, and that's sort of an edge case. You can handle it or not handle it. It's up to you. So what do we do in each of these cases?
So when you say spike, it means
Action potential, like the neuron has reached its threshold and it has emitted an action potential, which is electricity, which travels down this axon. So it depolarizes, produces electricity, which travels down the axon and reaches the synapse, where that electric signal is turned into chemical signal, which crosses this space, this empty space where it's full of fluid and other things, but crosses this space and then is absorbed by the postsynaptic neuron.
So does the spike happen even when you're not running anything through it, or like, say like you're running, let's say, an image for the neural net, would it be spiking even before you run the actual?
No. So I think the larger question is, will it spike without any input?
Yeah.
No, it won't. Most of these models will not spike without input. There are a few types of models, a few types of neurons that we model that have what they call tonically active behavior. And what that is they spike no matter, their default behavior is constantly spiking. And when they receive input, they actually turn off. So they're kind of the reverse. But those are,
extreme cases.
they're found in certain parts of the brain, and generally they're inhibitory neurons. So their role is to turn something off constantly until they get input, and then they pull back and allow whatever that thing is on the other end to increase in activity. So,
if it's dependent on the input, isn't it going to be like hard to see like the isn't the order in which they spike going to be dependent, or are these all be in the same layer, so to speak?
Yes. So if you had them in a feed forward setup where they're definitely layered, there's no recurrent activity, then you certainly, if A is in this layer and B is in this layer, I mean, A is not always going to spike before B, because a lot of the times when you model input's modeled, with whatever, a 0 to 1 value.
Yeah.
So if that was then given a weight, maybe B is also connected to C in the previous layer.
Yeah.
This one's getting a really high value. This one's getting a really low value. So this causes B to spike, but then slightly later this spikes because of its lower input. So even in a feed-forward situation, you can end up where the stuff downstream spikes before the stuff upstream. What we say is if the upstream neuron spikes before the downstream neuron, then you make this assumption that the upstream neuron's action contributed to the reaction of the downstream neuron. So A caused B to spike. If B fires and A fires later, then you say that B fired for some other reason than A's input. So you make the assumption that A played no part in B's spiking. And then if only one of them spike, you say, well, the shared synapse, which is the important part, played no role in this. And if none of them spike, then there's zero activity, so who cares? And so what you do is I threw my little function down here so we can, oh, there you go, now synapse is up there. This is probably the most common, and I think I pulled this out of another slide, so you can kind of ignore the values. But it's just an exponential decay function, right? Typical, here's your time window. This difference is the difference in spike between A and B, the time difference between the two. So obviously, if you're doing one of these cases, you'd flip this so that you get a positive number here. So it's either B minus A or A minus B. So that's an exponential decay. So what it looks like is you have this function that's two-sided. You have, I wish I had something to draw.
Are there any drivers?
Yeah, this says whiteboard marker. Let's see. Not that it will be visible, but so you end up with a function that looks like this. So if there's positive behavior, if there's heavy in behavior, whereas if there's anti-heavy in behavior, you know, it's like that. So let's say if A spiked, then B spiked afterwards, maybe here's the time difference. So this is the value by which that synapse would increase, whatever that is. Then multiplied by 0.01 in this slide is the learning rate that I just happen to have, whatever you want. And then, you know, you can have a different forgetting rate. So if B spiked before A, then you would sample from this side. And this would be the value by which the weight is compressed. Pretty easy. Very, like, you see that everywhere, spiking neural network and stuff. This is probably the most common way of learning. And it has a lot of problems.
Maybe B spiked before A because B is one of those all-time spiking neurons, and it shut off when A was sending a signal.
It's hard. It's hard, but if you notice, one of the things is that it makes a lot of assumptions, right? First of all, it's an extremely local view. If you've got thousands of neurons, you're doing weight modifications based only on spike times of two neurons connected to each other without any global information. It's a completely unsupervised, and not just unsupervised, it has no view of the rest of the network at all, right? So here, yeah, some of the assumptions that it makes this assumption that a connection between two neurons cannot belong to two different, or one neuron can't belong to two different subnetworks, distinct subnetworks.
That's an assumption.
That is an assumption I believe that this makes. This is my opinion, honestly, untested opinion. In other words, you know, not to do more whiteboarding, but I love whiteboarding. It sort of makes this assumption that if you have a neuron and you have one coming into it, that you don't have something like this, sort of a two-dimensional thing. So if you're moving information this way and you're moving information this way, these two paths are interfering with each other's learning.
So,
and that probably doesn't come into play so much where people use these for AI and data science, but it definitely comes into play when you try to do anything with a recurrent nature. What else do we have? So yeah, by nature unsupervised. Again, yeah, credit assignment is one of the real big biggies in here. So all of this stuff is running in simulated real time, right? An artificial neural network, you give it input and it's atemporal, right? Everything runs out and you get some output, right? These things run in real time. So as you're turning the crank to update these neurons, milliseconds are passing, but you may not get any kind of output that is useful until you've updated the network 1,000 times, right? Because activity has to bubble up here, and then you produce a spike, and then that goes to the next one, and you produce a spike, blah, 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 blah. And so once the input comes out at the end, let's say if it's even intelligible and it's wrong, how do you assign blame for all these other neurons? You say, well, 350 milliseconds ago, you spiked and that was wrong. You shouldn't have done that, right? It's a really hard problem to solve because there's no way of backtracking easily what caused what. There are a lot of little tricks people use. Some people use this equation to tack on a trace, a change trace, this two-sided Hebbian learning equation, a change trace, so that when they determine in a supervised way that the input is wrong, they go back and look at how much positive accumulation has been, negative accumulation has been, and then make a credit assignment later with some sort of decay. None of it works really well.
Oh, this might sound really weird, but could you try wrapping it in reinforcement learning? Like say have RL at the end and then like have a reward, some type of reward function, and then kind of use one problem to see the process or something.
Yeah, possibly. I believe there's some people who've done that. There's a lot of research and a lot of people who trying to use these. Yeah. They use traditional AI techniques, yeah, even traditional neural networks that they train and then try to do a transfer of those weights onto a spiking neural network. Yeah. And stuff like that to try and figure this out. Yeah. That's not really my area. Like I've not gone down that, let's do it the other way and then stick it in to the, but it's definitely turned out to be a very legitimate way of handling learning. It does work. It's a little clunky in having to do one domain and then go, well, no, let me stick it over here.
And then do those generally perform better when they're on spikes or?
Benchmarked against ones that were trained only using this type of learning or some derivative. Yeah, definitely. They've done a lot. I don't know about better. It's all situational because spiking neural networks, they have to do a lot of tricks in order to make them work for the cases where artificial neural networks do stuff very easily. Yeah. One of the things I've seen is since backpropagation of learning is impossible pretty much in spiking neural network, what they do is they only train the last layer. And they require the network to only emit one spike. So the first thing that emits one spike is the winner, and they only train the last. And at least for some of the things like the image recognition and the handwriting recognition databases that everyone tests on, I think some networks have gotten above 99%. A few of them, but they're nowhere near the like 99.9 to whatever percent that the other ones have, the traditional neural networks, artificial.
Yeah. I guess that's why you're kind of wondering, would there ever be a benefit to say like trying to incorporate a spiking thing?
At this point, no. No, if someone wanted to say I'm going to do data science or I'm going to make a classifier, I would say don't use these. So that's, for one thing, there's not a lot of tools to use these things, and not a lot of AI based and data science tools. A lot of this stuff is computational neuroscience spun. Also, yeah, so the other thing is that this learning process ignores a lot of very important things that the brain does that happen in the biological process, which one of my theories is that we've seemed to relatively easy, if you go back and remember that plot where the real and the fake neuron were spiking together, we seem to have been able to create differential equations that model how neurons behave really well. But we have not been able to come up with the way that they interact together. So great, we have these individual things which behave like real neurons, but our ability to connect them together in a way that's useful is very lacking. That's my opinion, at least. So yeah, this process ignores synaptic fatigue, like what I was talking about, where if one neuron just spikes all the time, the synapse doesn't do what it does in a simulation where you just have, your weight just explodes to infinity after a while. The synapse just shuts down. Neurotransmitter, there's like the diversity of neurotransmitters like dopamine and all these other things. The location along the connection, so dendrites are these big trees that stick out behind the neuron, so it depends on where they actually connect. If they connect really close to the cell, then a spike to that synapse will have a high chance of causing a spike in the post. But the ones that's connected very far away, that energy may never even reach the downstream neuron. It may just sort of dissipate in the distant dendrite. So too simple even for AI. I don't know what that means. I don't know why I wrote that.
Your functions are making it more trivial.
Yeah, I think I meant to say that it's that we haven't figured out enough to use this for AI. Like the first use of this is to model the brain, but we haven't figured out an even simpler version of spiking neurons that can be used for practical purposes that outstrip the artificial neuron. So what are they good for? Yeah, in my opinion, it's an open question because artificial neurons make better classifiers. Spiking neural networks are more computationally expensive. There are few AI-centered general purpose tools. There are no solid full network learning algorithms. I would say 3/4 of the papers that I've read about AI research using spiking neural networks train only a small part of the network, like the last from the last layer to the output layer to the output itself. Input and output are non-trivial to a spiking neural network because in a artificial network, you have a softmax layer at the end and you get a nice little float value or double saying, with 98% probability, this is a cat. But in the output of a spiking neural network, what do you get? You get, that neuron spiked 15 times, and that that one spiked 5 times and then stopped and then spiked 5 more times. What the hell does that mean? Right? And that plays into the last thing, spike time encoding, which is, in my mind, the kind of holy grail of all of this. Because traditional neural networks are rate encoders. So they take in values that are approximations or abstractions, if you want to see it this way, as the number of spikes that are happening in this part of the network. So if the value is 5 versus another one that has a value of 3, the one that has a value of 5 is spiking more than the one that has a value of 3. But in spiking neural networks, the time matters so much. When 2 spikes arrive matters so much. So how do you encode things into a spike train? A spike train that may be a spike at 20 milliseconds, then 100 milliseconds later, then 2 milliseconds later, then 50 milliseconds later. How does the brain encode, a cat?
That's complication.
It's an extremely complicated thing, and no one knows how that. We've come up with some fakey things, but to do input, but none of them are real, and no one knows how this works. But if they can solve this question, we can solve this question, then you get so much. So, like the second bullet point, if you can get spike time encoding, then power efficient computing. You can run a computer that can encode things like the brain. Our brains use an incredibly little amount of energy for the amount of processing power compared to an equivalent, server farm that gobbles up the kilowatts, right? So my personal opinion on this is that the best current use, and when I say current, I mean research now for the next 5 or 10 years, is things that require the integration of time and data. So unlike static pictures or unlike streams of things that you can cut up into nice little chunks, like speech, where you can kind of cut up the words, or you can cut up other things, or film, where you can cut it up into, stills. Something that would truly require a ton of data processing as time is progressing, and time itself is a factor in the meaning of what is being seen. And I think these,
given the time interval, the interpretation of what's being seen.
yeah. So if you were to take a still of a man standing there, and then you were taking the still of a man standing there, the same man, right? And that's just as fast as the camera. The meaning of that is possibly completely different than if you had a classifier that could take in the input of the man moving out of the room. Is that man entering the room? Is that man leaving the room? Did he just rob everybody in the room? What is this person actually doing in this room? And it's time dependent, right?
You think it would be good for some of the kinds of stuff we have in NLP is like really complex sequences. I don't necessarily say it would be time, but for instance, question and answer, and we're trying to extract a very specific answer from say a paragraph of information in the word context, or we're trying to map, say, user utterance given a dialogue history or something to some output utterance. Using spiking neurons could better model that, or
I think in some cases, yeah. I mean, it's a open research question for sure, but some things in NLP where I don't know. That's a good question, because one of the big problems in NLP is the sequence of the words and how far things are away, and stresses on words and pauses in words, and if we're talking about. I think so. I mean, maybe there's literature out there, but I haven't read a lot of literature of spiking neural networks being applied to NLP.
Yeah, well, and that's why it's very common in NLP. We essentially devise all these different types of attention methods to focus on various things. Again, soft attention and hard attention, various ways of training those. But do you think this might be weird, but could you actually infuse say attention with spiking neuron?
It's part of my research is, let's see how far it goes away. Yeah, so this is something I've been working on for a couple of years. It's a model of working memory. And this is more computational neuroscience stuff. One of the aspects of this network is that it has a bifurcated cortex. And so one part of the cortex models visual input. So let's say you show it a letter A or something. The other part of the cortex is modeling internal, what they call either executive control or attention. It's a real far out there theoretical concept, even in brain science, of where does that come from? Where does our conscious attention come from? And I model it with just the second separate part of the prefrontal cortex, that if I show something, two things, I can then turn on part of the attention network to say, well, the network is paying attention to only one of those things, or paying attention to both of those things, or it switches attention halfway through. And that has turned out to be very important to modeling short-term memory in spiking networks.
Well, yeah, and it's interesting, just because I know we have essentially we create in NLP. I mean, for a lot of things, we actually almost have to create and encode a type of memory for various terms, particularly in dialogue state tracking. We encode almost with the neurons, kind of a key values, not necessarily in the neurons themselves, but we have kind of an outside key value stored. The neurons actually going to reference when generating responses.
It's like context type stuff.
Yeah. So I mean, it's in any kind of dialogue. So you have a chatbot, each dialogue term, you're going to want to encode what the user says and then your bot's response into kind of a memory base along with kind of a knowledge base. And then basically using an attention mechanism, you would select which of those kind of previous terms in the dialogue is most relevant to the current term in generating the response.
I mean, my stuff is this is far more model-y type stuff than actual AI, but yeah, I think that attention, and I mean attention in AI is right now one of the hottest topics, I think, as far as how do you model it, how do you do it. And the neuroscience community is sort of the same way. Almost any process they want to model, you have to somehow come up with a way to do attention, because it governs everything. We're not reactive agents. In other words, like we don't see something and then automatically respond if there's a choice.
Yeah. So most of everything I've seen is mainly from a statistical approach. Like it's like a linked variable perspective, where you're trying to have some variable and see how it maps. And that stuff's interesting in itself, but I'm just kind of wondering if you could choose some of this.
And as far as attention goes, well, I mean, one of the easy ways is I wouldn't say easy, but I shouldn't say easy, but one of the obvious ways to start is that these things do have a sense of history, and the synapse, weighted synapses have a way to model recent activity. So you can string that out. You can have the decay far slower and tweak it so that when activity happens, decay rate goes off at this certain amount. One of my other, actually this project, I don't have it in here. It's mentioned in the second half, synaptic plasticity, but this model relies on two different, it actually has no weight changing capability. What it does is it changes potentiation values, which work like weights, but they're not permanent. So they decay. So all activity ceases, they slowly tail off. And there's two of them that decay at two different rates. And I have just in the last couple of weeks, I've been asking myself, why do I need two different decay rates? And as it turns out, one of them, if you don't have a fast decay rate, the network can't forget anything, because whatever it sees, it just remembers for a very long time. But if you split this potentiation of the synapse between a very fast value and a slow value, then it is able to remember stuff for a long period of time. But if it needs to switch, do a sort of a context switch to something else, then that fast decay pushes the synapse values, the weight values, down below a threshold to where they'll no longer be relevant to new activity. Or a new activity will override them very easily.
Yeah, I remember that from continual learning when I looked at it. I mean, we didn't do exactly the same stuff, but for instance, there was like this thing in continual learning of hard attention to the task. Well, it would like make certain weights not modifiable, and other weights modifiable. Basically, it's going to try to learn through hard attention which weights were most important for which task. This is just in the classic and then not modify those, but just modify the other ones for subsequent tasks.
Yeah.
Which is kind of sorry, kind of
No, it's fine. That's where the best part of all of this comes, is when you sit around and I guess I'll go, since I was on that. This is just a sample of like the output of some of my work. So this is taken from what I call a 2-item working memory task. And this is just so you can see spiking behavior. The network I run can handle remembering 15 different items, or it has the ability to remember 15 items.
It took a while to spike.
What's that?
It took a while to spike because
the second one.
Yeah.
So what's happening here is this is really, really suited, and I'll demonstrate at a human level what's going on. I have a green and an orange, right? So I'm going to show you one, and that's the correct one, right? So there's the correct one. Which one is the correct one? This one, right? So there was your working memory task.
You said green.
Oh, did I say green? Well, you pointed at this one.
Yeah, I thought you
So-
were testing me
No, no.
because you called orange. as
Orange
green.
green. That's my inability to see that. So you passed, but that's what I'm doing with the network. So these are two different. These are neurons which are capable of remembering two different things. So this one was shown an item here for 1 second, starting at 5 second mark. These are milliseconds. And after 1 second, the only input to the model is attention. So it's paying attention to this one thing. As you see, because of the change in the weights of the synapse, the potentiation, you get this burst spiking. So this consistent activity throughout. And so then here at the 11-second mark, so it remembers it for 5 seconds, the 11-second mark, you show it a distractor item, the incorrect item, and the correct item. And it's supposed to choose which one is correct based on the activity that these two things produce during this 1 second choice phase. And the network, when it's all fully connected, will make the correct choice like 98% of the time.
So how did you design this experiment?
You mean the task itself? It's a sort of a classic neuroscience task to test working memory. It's extremely simple. It's dumbed down for the computer, but there are very similar ones in neuroscience where they test your working memory, where they show you 4 things, and then we'll show you a subset of those or something like that, and say what's missing. Ask you to change one, say, here are 4 things. Now replace the Q with an R, and then make you wait, then say, okay, now tell me what those letters were. Or something like that. This is sort of a similar working memory task. This just shows how memory is stored. It relies on synaptic changes and on this continued activity. So there's actually no input into these neurons at this time.
Oh, wait, okay.
So the input only happens here.
Okay.
And the network is highly recurrent, right? The connections are recurrent. So its own activity with strengthened synapses are causing this activity to continue down the line until you reach the final part. So, I have a couple other projects. I made a little C++ library that puts some of these neuron models into very simple C++ libraries with the idea that if someone wanted to put them into a project that was non-neuroscience-y, you could just take these 3 or 4 C++ files, throw them into your project, and add in some neurons to your project for whatever reason. It comes with a bunch of synapse models that do this type of learning, some other weird models that I came up with. And a project I've been working on for the last month is doing a model of the hippocampus specifically for AI.
What's hippocampus? Sorry.
It's a don't worry, I'm gonna get to it. It's a part of the brain that has been shown over the last 30-40 years to contain a strong sense of spatial information in the brain, so internal spatial information. So there's a thing called place cells in the hippocampus that basically they reorient when you enter a new environment. But whenever they reorient, if a place cell fires when I'm standing here and I walk to the front of the room and come back, that same cell will fire when I reach this location. And they have fields of some distance. So they map onto real spatial places. There's also grid cells, which always fire in a hexagonal pattern. So if you move, and they're always oriented in a certain way. So if they orient, let's say this way, and I move this far in this direction, it will fire again. So they always fire at these hexagonal points in space. They can reorient, can stretch, can come back together. There's cells which fire whenever you're facing certain directions, which also are oriented not north to south, but based on visual cues in an environment. So I started working on a project that will create an AI version of the hippocampus to do exploration in an unknown environment of an agent using these types of neurons.
Or you said you might use it in the context of lifelong learning.
Yeah, that's exploration in the context of lifelong learning. I want it to be exploration in a dynamic environment that starts off unknown and can change. In other words,
Okay. Yeah.
that's my interest, and it would be based solely upon visual cues and this internal mapping system that seems to exist in rat brains and human brains and monkey brains and all mammal brains and rodent brains. Yeah, so I guess that's.
Yeah, I just found that interesting. Like some of what I do. Well, one of the papers I was trying to publish for a while, the state was one of the right now, was the first kind of like study of continual learning for NLP. So I was thinking a lot of particularly sequence to sequence models for like neural machine translation, also slot filling and dialogue.
Is this the what you were working on like 6 months ago?
Yeah,
that you were talking about. Okay.
Yeah. So when I was then trying to study, like I would like start on like say a task of slot filling dialogues in the restaurant context where you have like the restaurant price and these different slots you need to fill into, then train it on say like you're booking an airline ticket and then like I don't know, even schedule surgery or something, a diverse array of tasks and see then like if it could still perform the first task. Yeah. Nice. So yeah. What?
Could you repeat that?
So it's like basically you have continual learning is the idea you have a series of tasks, and basically you want to you want to minimize what is called catastrophic forgetting, which is backward transfer. So sometimes when you learn a series of tasks, a neural network learns a series of tasks, it can't remember the first task because as you train it, it becomes optimized for the subsequent task. So you train it on say, a more simple example would say be like you first train a classifier for dogs and cats, then you train it on say lions and tigers, and then say like on elephants or something. And over time, it will be able to remember dogs and cats and stuff like that. So there's a whole area of research in neural networks called overcoming catastrophic forgetting. So what I was doing, it's mainly been all in kind of image recognition type problems. So what I'm doing is doing kind of the first study to apply it to NLP problems. So I'm looking at a variety of different tasks in both kind of slot filling and also neural machine translation in other areas like that, where say first you might train a model. Well, let's just use neural machine translation because it's a little easier than slot filling. But first you might train a model to translate, say like English to Spanish. Then you might train a model to train it next to translate English to German and English to Japanese. Then you want it to say you were Google Translate, you still want it to be able to translate like English to Spanish. I mean, that's not really exactly how it works, because in reality, these are all trained in a very multi-task way anyways. But the idea is the same. So like if you have, say, like a chatbot, you might slowly add new types of slots, labels, and capabilities. So say like your airline reservation system, you might start off just doing airline reservations, but then you might also do bus reservations. So you want to be able to train your model to now do bus reservations without having to entirely retrain all the reservations because it's expensive to retrain. You might have lost access to the data. So it's kind of important for the industry.
And there's no guarantee that retraining it on airline data might make it forget the bus data that you just trained it on. Yeah, that's the thing with neural networks is they're sort of one, like there's a lot of ways to branch them out, but there's generally in the purest sense they're a one-shot thing. Still today, you train them to do one task, and they're damn good at that one task, but they're not going to do much else for you.
Yeah, I just thought if you just add more memory to
it is one of that dynamic architecture is one of the ways that people have tried to overcome that. Just the problem is that it doesn't scale well with new tasks.
Well, and also they've seen that like that also if you train everything on the same time, say you have both bus and airline data at the same time, if you trained out both at the same time, it would in general perform well on both of those. But the problem times when you sequentially train on different tasks, it's like almost like invariant domain adaptation. So it just adapts to the new domain without previously remembering the old one.
Yeah.
And kind of on the flip side of that, another thing I study is meta learning, which is actually purposely training it for task adaptation, where you train it on a bunch of different tasks in order to get the maximum forward positive transfer. So I might train it on a variety of tasks, and specifically to create a set of weights that then when I train on a new task, it adapts very rapidly to that when I might only have like 5 or 10 examples from that task. So they're almost kind of opposites of each other. One's trying to maximize this forward positive. Well, not exactly, but one's trying to maximize forward positive transfer. The other one's trying to, you're still trying to have forward transfer, but you're also trying to not have backward transfer.
Yeah. Well, unfortunately, all the stuff we talked about here today is not going to help with any of this. So, thanks for showing up. I like talking about all this. I find it fun, you know, otherwise I wouldn't work on it, I guess.
Yes.
So,
Definitely thanks for presenting tonight. Zach.
no problem, man.
Very interesting.
Yeah, I got into it very much by, I would say, accident in some way.